Hello out there, everybody. Manny here at Area 503. And you'll have to forgive me, I'm just getting over a little bit of a cold, but I just couldn't wait to get this video out. Today I just want to talk a little bit about neutrinos. And more specifically, about an ice cube who's chillin' in Antarctica. No, not that one. This one. The Icecube Neutrino Observatory, located at the Amundsen Scott South Pole Station in Antarctica. Let's take a look at these short clips that talk about the Icecube project.
Icecube is best known, of course, for detecting cosmic neutrinos. It's amazing that Icecube detects neutrinos all the way from 10 GeV to 10,000 TeV. And somewhere in that energy range, we actually have the opportunity to detect sterile neutrinos. What we can do is measure oscillations of neutrino beams coming through the Earth. What's special about the Earth is that the neutrinos interact with matter. And if they spend some of their time as a sterile neutrino, then these oscillations are slightly changed. They are retuned to the fact that at some specific energy, they make a resonance. And this is a dramatic effect in the data, which you either see or you don't see. It's as simple as that.
A sterile neutrino is a hypothetical fourth type of neutrino, and it has a few important properties. Among those important properties are that it has mass, and that mass is different from the masses of the other known neutrinos. The other important property is that the sterile neutrino interacts only gravitationally. Because it's so non-interacting, that makes it rather hard to detect. However, we can see the effects of sterile neutrinos in the way they influence the behavior of the other known neutrinos.
We have this amazing beam of neutrinos created in the atmosphere by the cosmic rays, and Icecube sees one of these neutrinos approximately every 6 minutes.
The idea is very simple. Icecube detects atmospheric neutrinos over a wide range of energies with a peak at around 1 TeV all the way up to hundreds of TeV. These are actually an annoying background to the astrophysical searches that Icecube was designed for. But they're also a great tool for studying particle physics.
The sterile neutrino changes the amount of mu neutrino via the neutrino oscillation phenomena, and that basically is related with when the neutrinos propagate, they change flavors from one to another. Then adding a new flavor, it may produce the mu neutrino going to this sterile flavor and disappearing.
It turns out that it is more likely to morph into a sterile neutrino if it goes through a very dense region of matter. And so the core is ideal for producing much more morphing than you would get if for the neutrinos that do not travel through the core. And so what we're looking for is we're looking for neutrinos that are on the trajectory that comes through the core to disappear.
Okay, so neutrinos are high-energy particles most commonly put off by our sun. And there are 4 different kinds of them, including the theoretical sterile one. And the Icecube Neutrino Observatory uses 86 sensors such as these to detect these neutrinos as they pass through the ice. So now that we know what neutrinos are and what Icecube is, this next clip is going to make a little bit more sense. In a press release dated July 12th, 2018, NASA states Fermi traces the source of cosmic neutrino to a monster black hole. NASA then released this video. Let's go ahead and watch it. We'll come back and talk about it.
For the first time ever, scientists using NASA's Fermi Gamma Ray Space Telescope have found the source of a high-energy neutrino from outside our galaxy. The neutrino came from the eruption of a supermassive black hole at the center of a type of galaxy called a blazar. The eruption jetted out particles moving near the speed of light. Collisions inside the jet produced gamma rays, the highest energy form of light, and neutrinos, ghostly particles that rarely interact with matter. 3.7 billion years later, they reached Earth. On September 22nd, 2017, a single high-energy neutrino struck an atom in a water molecule in the Antarctic ice. The crash produced a particle called a muon. it raced through the ice so fast it emitted a faint blue glow. When the muon reached the South Pole, it was tracked by the Icecube Neutrino Observatory. Icecube scientists found the original neutrino likely came from beyond our solar system. They alerted astronomers to be on the lookout for cosmic outbursts possibly associated with it. NASA's Fermi Gamma Ray Space Telescope found the source, a blazar it had been watching for some time. When the neutrino arrived, Fermi saw the blazar was brighter than it had been over the previous decade. It's the first time a neutrino could be traced back to a black hole, or to any source beyond our immediate galactic neighborhood. And it's an important step forward for a growing field scientists call multi-messenger astronomy, which combines light with new signals like gravitational waves and neutrinos to provide new insights on the most extreme cosmic phenomena.
September 22nd, 2017. Icecube is running daily operations when they detect a strange trajectory for a neutrino. An alert is sent out and Fermi is trained on TX0506. Now this is an actual visualization of the gamma ray bursts from blazar TXS0506. And as you can see, there is heavy activity. One more interesting thing to note. In both the press release and the video, NASA stated that the neutrinos and gamma rays had traveled 3.7 billion light years at almost the speed of light. However, TXS0506 is 6 billion light years away from Earth. This could simply be a mistake on the part of NASA, or it could mean something else. Quite frankly, I like the idea of a particle that can move faster than light, which could lead to all new kinds of science.
Warp drive, Mr. Scott.
Well, folks, I truly don't know what it all means, but that's not going to stop me from trying to learn. And that's everything I have to share with you on neutrinos, Icecube, blazars, and gamma rays. This has been Manny SixFingers at Area 503, and I have enjoyed our time together today. Until next time, I wish you all the best, and I'm out of here to continue on my search for universal truth.